Matrix communication challenge. Imagine a mathematical rule that works perfectly until it doesn't. This is the incredible story of matrix traces that defies expectations. In problem 17, we're tasked with prove that the trace of a product of T1, T2 is equal to the trace of T2, T1. It follows immediately that the trace of T1 times T2 times 3 is equal to trace of T2, T1, T3. But in this case, is it the case that the trace of this product actually equals this product? In general, prove it or disprove it. Now, the question gave us a hint. The best disproof is always a counterexample. The simpler, the better. So that should be enough of a hint to show you what's going to happen with this one. Now, as far as the trace product of cyclic invariance goes, the trace of a matrix is a fundamental concept in linear algebra defined as the sum of the elements on the main diagonal of a square matrix. For a matrix A, it is expressed as trace A equals the sum of all matching indices indicating the main diagonal terms. A key property of the trace is its cyclic invariance for the product of two matrices. This can be demonstrated as follows. So when we're taking a product of two matrices T1, T2, and we're asking about the trace, well, we need all the terms of the product main diagonal. But we know that the product here looks like the dot product of specific rows with specific columns. So that's what we see here by introducing another summation sign over J to indicate all the rows. That being said, we have the row column kind of construction here. If we want the inner dimensions to match and the outer dimensions to be the result, this is what we have to have. As a result, by switching these two to where I have the inner dimensions now being I and I, the outer dimensions being J and J, that can happen so long as I switch the summation over here. As a result, I now take the product of T2, T1 with the inner dimensions I and I going away, the outer dimensions J and J staying put, and now it looks like I have the trace definition for T2 times T1. Pretty darn cool. Now, this property is crucial in various applications of linear algebra and quantum mechanics. For example, consider the density matrix formalism that we covered in chapter 12. However, there are limitations of this trace property. And it's important to note that the cyclic property of trace does not extend to arbitrary permutations of matrix products. The property here does not generally hold. A notable counterexample is provided by the Pauli spin matrices, where we have T1, T2, T3 defined by the spin X, spin Y, and spin Z matrices respectively. And what we see here is that by setting up the products here and just chugging out a couple calculations, we see that T1 times T2 times T3 takes this form. T1 times T2 leads to this purple matrix, row to column, find all your matrices elements. And then we see that we have this matrix that needs to be multiplied in. Upon doing so, we obtain the matrix I00I, which if we calculate the trace is the sum of the main diagonal terms. So that's just I plus I, which gives us a value of 2I. Now, if we switch the location of T1 and T2, as we see color-coded here, switching green and blue respectively, we see that the purple matrix of their product is equal to negative I 0, 0I. So the negative sign switches on these i's here. Multiplying this again with the sigma z matrix or spin z matrix leaves us with negatives on the main diagonal. So taking a trace of that, we're adding two negative i's together, leaving us with negative 2i. As a result, it's clearly evident that this first trace does not equal the second trace, so this property doesn't hold. And so this counterexample underscores the importance of understanding the limitations of the trace property in matrix algebra. It has significant implications in quantum mechanics where these Pauli matrices play a crucial role in describing spin 1/2 systems, as we've seen time and time again in the quantum mechanics book. So quick video, but a fun, impactful one. Because of the density matrix formalism, this is used quite frequently. Remember, the expectation values were given by the trace property of the mixed state matrix formulation. So if this video got you thinking, imagine what's coming next. Subscribe and join our community for weekly insights into the world of physics. There is so much more to uncover, and I'd love to have you along for the journey. I also just want to take a moment to thank my incredible Patreon supporters. Your support is truly the backbone of this channel. It's because of you that I'm able to keep creating these videos and diving deep into the fascinating world of physics with everyone. Your contributions make a real difference in helping me bring these concepts to life, and I'm so grateful to each of you for believing in this journey. And if anyone else is interested in supporting the channel and joining our Patreon community, you can check out the link in the description below. Together, we can keep exploring the wonders of science and discovering even more amazing things. As always, thank you for watching, and until next time, stay curious.